Welcome to the fifth lecture of the course Turbulence. So as usual, let's start with some recap. So in the last class we started talking about the inviscid instability, that is Rayleigh's equation. So we mentioned that in the limit of very small viscosity, the limit of very small viscosity or infinite Reynolds number, that Schwarzschild equation can from the Schwarzschild equation we can find the Rayleigh's equation. That's what we have started in the last class. So let me again start with this. So u minus c, this is phi double prime minus alpha square phi u double prime is equal to minus I alpha re phi minus twice alpha square phi double prime plus alpha to the power 4 phi. Okay, so this is what is our Schwarzschild equation. In the limit of very small viscosity or infinite Reynolds number, this particular part vanishes and we eventually get the Rayleigh's equation, that is your let me just write it once again, minus alpha square phi, taking the u minus c term here as we wrote in the last class, u minus c is equal to 0. So this is what is our Rayleigh's equation. Okay, so and boundary condition for this, that phi is equal to 0 at extreme boundaries, that is at, let's say, A and B. Okay, so this is what is our Rayleigh's equation. And then what we did, that we have multiplied this equation with complex conjugate of phi, then integrate the equation between these two boundaries. Okay, if we start with that, then we can write, so multiplying by complex conjugate of phi, which is phi star, we can write this equation as that phi double prime phi star minus alpha square phi square, because phi star and phi, which is nothing but this absolute value of phi. So let me remove this one, it's not necessary, and then minus, once again I can write this as this u double prime u minus c is equal to 0. Okay, then we have integrated each and every term from one boundary to the other boundary, that we have considered minus infinity to infinity in the last class, considering free shear flows. But for more general case, we can consider two extreme boundaries, and then we can get. So let me again write it. So integrating this equation, okay, we get the following. So integrating from from one boundary to other, so that we write this as phi double prime phi complex conjugate, then dy minus a b alpha square dy minus a b phi, absolute value of phi, then u double prime, this is your u minus c dy is equal to 0, right? Now integrating by parts, okay, of this particular term, we can write this as phi star, okay. So because this is the first function and this is the second function, so phi star integration of this, so this is in the boundaries, okay, so which gets cancelled, okay, and we have then a to b here, so this is your phi prime and phi prime star, right, dy, the other part of this integration, okay, minus this one which is a to b alpha square y square dy minus here what I can do a b, here what I can do, I can just multiply by u minus c star, okay, and u double prime, then absolute value of phi, and then I can write the lower one as this equals to 0, okay. Now this is 0, okay, so this particular quantity will be 0 from the boundary condition, so we get, you see, eventually a to b. Now you see that phi prime and phi prime star, so this can be written as, okay, this can be written as phi prime, okay, phi prime absolute value of phi prime dy, okay, plus alpha square a to b, then phi prime square dy plus, okay. Please note that there was a slight mistake in the last class, I forgot to take the plus at this point, it was minus in the last class, so please correct this, okay. So this is going to be minus, this is going to be your a b, and this is your u minus c r, then this is complex conjugate, so plus I c I, okay, then u double prime phi dy, then u minus c square, okay, dy, right. All right, or you see this equation, sorry, there will be equals to 0, okay, I am sorry, okay. So this equation will have two part, one is real part and another is your imaginary part. So the real part of this equation, let us write the real part of this equation, if we write, that is going to be your plus alpha square phi dy plus u minus Cr u double prime u minus c absolute value of this dy is equal to 0. This is the real part and another part will be imaginary part. Okay. So, that is going to be your essentially C I. So, that is C I A to B u double prime absolute value of phi u minus c dy is equal to 0. Okay. Let us call this equation to be equation 1 and call this equation 2. Okay. So, let us consider the equation 1. In equation 1, for C I non-zero, this integral has to vanish, and this integral to vanish, the u double prime has to change sign in the flow domain, otherwise cannot vanish. Okay. So, this is what is the Rayleigh's theorem. Okay. So, for C I not is equal to 0, this integral has to vanish, and this integral to vanish, that u double prime has to 0. So, the theorem 1, as we mentioned in the last class. So, theorem 1, that is your Rayleigh's theorem, so that is, it is necessary for instability that the velocity profile, it is necessary for instance the velocity profile has a point of inflection. Okay. So, this is what is the outcome of this imaginary part. Okay. So, this theorem needs to be carefully applied. So, what it says, it is necessary for instability that the velocity profile has a point of inflection. The converse is not true. That means, we cannot say that if there exists a point of inflection, the flow will be immediately unstable. We cannot say that. Okay. So, but if the flow is unstable, if the flow is immediately unstable, then it is necessary the velocity profile has a point of inflection. However, the negation of the theorem is true. For example, if there is no point of inflection in the velocity profile, then the flow is stable. Okay. So, this is true. All right. So, this is what is the Rayleigh's theorem says. Okay. Now, that another point we will get from the real part of this. So, the second theorem, so let me just state that theorem. Second theorem, okay. So, that is due to fiat of okay. If there exists a point of inflection, it is further it is further necessary that u double prime u minus u s less than 0 somewhere in the flow domain. Okay. So, it says if there exists a point of inflection, then it is further necessary for instability. It is further necessary for instability, please correct it. Further necessary for instability okay. It is further necessary for instability that this is less than 0 somewhere in the flow domain, okay, where u is equal to u s is the velocity at the point of inflection. Okay, y s. So, this is what is the theorem of or second theorem of inviscid instability. Okay. We are at present discussing the inviscid instability. Okay. So, this is a stronger form of this first theorem. So, first theorem says it is necessary for instability that the velocity profile has a point of inflection. Second theorem says if there exists a point of inflection, it is further necessary that this particular quantity should be 0 or less than is equal to 0 somewhere in the flow domain, where u s is the velocity at the point of inflection, that is y s. Okay. So, let us further discuss this, or first let us prove this, after that we will discuss. Okay. So, the first theorem can be proved from this. For C I not is equal to 0, this integral needs to vanish, and for this integral to vanish, that u double prime should be 0 somewhere in the flow domain. That means, there should be a point of inflection. U double prime is equal to 0 means that is the point of inflection. Okay. So, that is the kind of proof of the first theorem 1 or Raleigh's theorem. To prove the second theorem, what we can do? We can multiply C r minus C r minus U s divided by C I to this equation. Okay. So, equation 2 into C r minus U s divided by C I plus equation 1 if we do, with this modification we should be able to show the theorem 2. Okay. Let us do it. Okay. So, what we are going to do? So, C r minus U s divided by C I into equation 1, that is your C I integral u double prime phi d y u minus c, okay, is equal to 0. Okay. Now, we add this to equation 1. If we do that, so let us say this is 3. Okay. So, adding equation 3 with equation 1, we get, what do we get? Let us see. So, we get A to B phi prime plus alpha square dy plus, if we add this quantity, this Ci gets cancelled out, Cr, okay, and if you do this little bit algebra, you will be able to show u minus us square u double prime u minus c square dy is equal to 0. Okay. So, you see this particular part, okay, this particular part is positive definite, this is square, this is square. So, this integral is positive definite, and this particular integral then has to be such that the addition of these two is equal to 0. It can only happen if this u double prime into u minus us is negative somewhere in the flow domain, so that their addition will be equal to 0, because this is positive definite, this is positive, this is positive, that means u double prime into u minus us has to be negative in part of the flow domain, then only this summation of this integral can be 0. Okay. So, this is what the argument. So, that is the basically proof of this second theorem. So, that means that u minus us, okay, u or u double prime, this should be less than 0 somewhere in the flow domain, then only this above equation will be satisfied. So, this is what is the second theorem. That means, it says that if there exists a point of inflection, it is necessary for instability that this particular quantity is negative somewhere in the flow domain. However, the converse is not true. What is that? If this is negative, it does not necessarily guarantee the flow will be unstable. However, the negation is true. If this is not negative, the flow is stable. Okay. So, while applying theorem 1 and theorem 2, one needs to be very careful. Okay. So, that is the point, right. Now, let us see, let us try to understand this particular criteria as well as Raleigh's criteria for some given velocity profiles. Okay. All right, let us take some of the velocity profile and try to see based on this theorem whether this velocity profile is going to be stable or unstable. Let us take a first one. Let us say first velocity profile is something like this. Okay. So, this is your y and this is your mean velocity u or base velocity u, for example. Okay. And let us say this is what is your velocity profile. Okay. The first velocity, let us say profile A, okay. And let us say profile B, let us say profile B, we will take it here. Okay. Profile B, the profile B let us consider to be like this. Okay. This is what is your profile B, for example. This is y, this is once again u. Okay. Let us consider another profile, let us say profile C. Okay. So, profile C, let us say this is what is our profile C. Okay. Okay. And this is once again y, this is u. And consider another one somewhere here. Let us say that is this. So, okay, this is once again u and this is y. Okay. So, for velocity profile 1 or velocity profile A, there is no point of inflection. Similarly, for profile B also there is no point of inflection, whereas for profile C there is a point of inflection somewhere here. Profile of point of inflection in means there is a change of curvature. You see there is a curvature like that, after this point the curvature is going like this. So, it is something like this and here it is something like this. So, there is a change of curvature somewhere here. So, that means that u double prime should be 0 at that location. So, this is what is your point of inflection. Okay. Similarly, here also if you see there is a point of inflection somewhere here, change of curvature. Okay. So, this is this side and this curvature you see in this side. So, from this to this when it is going there is a change somewhere. So, at that location that u double prime will be 0. So, this is what is your point of inflection. Okay. So, that means if you consider this as per your theorem 1 and 2, this velocity profile is stable inviscidly. Okay. We are talking about inviscid instability, please do understand, because we have neglected the right hand side Rayleigh field equation. Okay. So, we are talking about inviscid instability. So, this profile inviscidly stable. What about this? Even this profile also same, because there is no point of inflection, whereas there is a point of inflection for this particular velocity profile somewhere here. So, according to Rayleigh's theorem or theorem 1, this velocity profile is unstable. Similarly, there is a point of inflection for this particular velocity profile. So, as per Rayleigh's theorem, this profile is unstable. But what about Piotov's theorem or the theorem 2? Is this profile stable or unstable? That means, for that you need to calculate u double prime u minus us. Okay. This quantity needs to be checked for this profile. If this is greater than 0, then as per Piotov's theorem or theorem 2, this profile is stable, and that is the case. We will see the value of this is greater than 0 for this case, whereas the value of this quantity u double prime u minus us, okay, less than 0 for this particular case. That means, this particular profile is unstable as per Rayleigh as well as Piotov or Piotov theorems. That means, as per theorem 1 as well as theorem 2, this particular profile is unstable, whereas this particular theorem, this particular profile is unstable only as per Rayleigh's theorem, whereas it is stable as per your Piotov's theorem. Why? Let us see. Okay. So, for this particular velocity profile, for example, if you calculate, if you plot y versus let us say your del or du dy for this particular profile. Okay. Let me do it somewhere here, so that I save some space. So, if you see, this is once again your y only. So, your du dy will be something of this sort. For this particular velocity, this is your du dy. You can understand that can be readily see at any location you keep your delta y same. For example, at these two location your this delta y is same. Okay. Let us say this is what is your delta y, this is why it is a delta y here. Okay. So, that means your this point is y1 and this point is y2, okay, and this point is u1 and this point is u2. So if you see du dy, which can be approximated as du delta u delta y. Okay. So you see delta u means u2 minus u1, which is positive, y2 minus y1, which is delta y, which is positive. So this value is going to be positive, okay, in all the places wherever you. But as you are going, towards the outer side, okay, you see somewhere here, if you consider your the same du dy, you see where your y2 minus y1 is the same, but your velocity difference is almost negligible here, whereas the velocity difference is more here, velocity difference is very negligible here, right. So that is why if you see here, the velocity difference is not that high like the one here. So here if you see, the velocity difference is pretty high, okay. The velocity difference is high near the wall, velocity difference is less as you go outer side of the wall. That means this curve has to decrease as you are going towards the outer side. So if this is the case, then what is going to be the double derivative of this curve? So double derivative of this curve, if you calculate anywhere, so this is what this is what is your delta y change, right. So this is the change of your delta y, you see, and corresponding change in this value, okay. Corresponding change in the gradient is this much, and that is going to be negative, because why? See, this is what? This is your y1 and this is what? This is your y2. So corresponding to y2, this is the value where your this let us say this quantity we call it u1. So u1 and so corresponding to y2 the value is u2, corresponding to y1 the value is let us say u1 or not, or let us say u2 prime and u1 prime, it is basically derivative. So you consider u2 prime and u1 prime, then you see, so there you see what is going to happen. That means for y2 minus y1, it should be u2 minus u1, which is negative. So what it says, the delta u prime delta u y, this is going to be negative less than 0 for entire profile. That means if you draw it here, if you draw it somewhere here, if you draw it here, then this is your y and it is going to be something like this, okay. So this is basically your d2u dy2 and this is what is your du dy, okay. So from this velocity profile you can figure it out that within the flow domain it is not changing sign, it is from negative it is going to 0, okay, somewhere in the free stream, right. For this particular case, if you consider now, for this particular case, similarly you can show for this particular velocity which you try at your hostel, okay. And for this particular velocity profile, if you notice that the velocity at that location is us, okay. So what is the value of u double derivative within this? It is something similar, this till this it is something similar. So that means u double prime should be negative for this, u double prime, because this is curvature just something this above velocity profile. That means below this point that u double prime is negative, but what about this u minus us? Below this point u minus us is also negative. That means this quantity is going to be greater than 0 below this. What about in this side? In this side above this point u minus us is positive. What about u double prime? That also should be positive, then only it can be greater than 0. Let us see. So, the above this particular point the velocity profile just like that. So, if the profile is like this, you see near the wall, let us say this is what is your delta y, then the corresponding change in velocity is this much only. So, this is what is your corresponding change in velocity. Okay. This is delta y. So, that means if this is your y 1, this is your y 2. So, y 2 minus 1. So, that means your derivative needs to be delta u divided by delta y. So, delta u positive or negative, this is y 2. So, u 2 is this, this is y 1. So, u 1 is this. So, delta u is positive here. So, delta u positive, delta y is positive. So, delta u delta y is positive, that means du dy is going to be positive. So, this is true for all these points. That means, if you draw that draw this value, so then you will see that it is slowly from the very minimum value. So, very minimum value it is increasing like this. So, this is the value. So, minimum is this, after that it start increasing. So, this is the value of du dy for this particular velocity profile. If this is the value of du dy, then what is the value for u, that double derivative? That is also positive. You see, if this is y 1, this is y 2, then this value is higher than value at y 1. That means the double derivative, of this is also positive. Okay. So, that means the double derivative is also positive. So, the double derivative for this particular profile, if you draw, it is also going to come something like this. Okay. I do not have much space. So, the double derivative for this case if I draw, then this is going to be positive as we have argued, and that value is going to something, like this. Okay. The value of double derivative is going to be, this is y, this is y 2. Okay. So, this is positive for this profile. That means, the double derivative value for this particular regime is going to be positive. So, this is positive, and definitely u minus ui, u is any point within this is higher than us, that means the velocity at that location. That means, this quantity is greater than 0 for this particular velocity profile. If you see in the similar argument, you will see this quantity should be 0 in the for this particular profile. So, therefore, we can call this particular profile is unstable as per theorem 1 and theorem 2, and this particular profile is unstable as per theorem 1, but stable for as per theorem 2. Okay. That is all the discussion. All right. So, this particular argument we have talked about solely based on in-sheet instability, okay, without solving any equations. Okay. Now, the point is that let us say your profile A and profile D, let us say this is profile D. Okay. So, this is profile D, CD. Okay. Now, let us say profile A and profile D. If you go ahead with viscous instability for these two cases, which profile will give us the minimum critical Reynolds number? You will figure it out if you go ahead with the Schwarzschild field equation. If you solve the Schwarzschild field equation for this velocity profile and this velocity profile, Schwarzschild field equation means it is not, it is viscous instability you are talking about, no more in-sheet instability. This argument till now we are talking about is in-sheet instability. Now, I am considering, if you consider this velocity profile as well as this velocity profile, apply the Schwarzschild field equation, that is your viscous instability, then which profile will give us the least critical Reynolds number, this is the one. Okay. So, let us see this. So, if you solve the Orshmer field equation for the velocity profiles given in C and D, then let us say the temporal instability problem you are doing. So, this is your going to be Reynolds number and this one is going to be your non-dimensional wave number alpha. Okay. If this is the case, you will see okay. So, this is your C I is equal to 0, this is also C I is equal to 0, C I is equal to 0. Okay. So, neutral stability curve. Okay. So, this is what your critical Reynolds number RECR, and for this it is the RECR is this. Okay. RECR. This is for profile this one, the one which is having point of inflection. Okay. So, this particular velocity profile so, for this particular velocity profile, this is y, this is your u and this is the point of inflection. So, this is what the velocity profile. Okay. And for this one is for velocity profile without any point of inflection. Okay. So, that means for this case there is no point of inflection within the flow domain. So, the moment there is a point of inflection in the velocity profile, you see the critical Reynolds number for that it is going to come down. Okay. So, this is C I is equal to 0 okay, for the velocity profile which is having point of inflection, and for that you see that because this is unstable on inside and stable outside, right, that is what we have learnt in the last class. So, that means the critical Reynolds number for a velocity profile with point of inflection is less as compared to the velocity profile without point of inflection. That means what it says, the profile which includes point of inflection, it is more prone to instability. That is why if you consider your jet, wake, shear layer. Okay. For example, if you consider a jet flow, jet flow comes like that. Okay. For jet flow profile, if you consider it is having a point of inflection. So, this is the jet velocity profile, the jet is coming out from there. Okay. Similarly, if you consider a wake, for example, you have a blob body and there is a wake. So, if you get the velocity profile somewhere here, then it is going to be if you consider the velocity profile somewhere here, the profile will be something like this. Okay. Okay. So, for this profile also there is a change of curvature, there is a point of inflection for both the cases, and for this case the Reynolds number RECR value is about 4, for this case also that RECR value is 4, for this case also RECR value is approximately 4. Okay. And for shear layer, for example, your that shear layer of this type, mixing layer, that is what we call it, shear layer. Okay. For this kind of profile, RE CR is equal to 0. Okay. So, since these all profiles
has a point of inflection, or since each and every profile has a point of inflection, their critical Reynolds number will be lower. That is what as per the expectation from this curve. Okay. That is what the case also, if anybody does the linear stability analysis. Okay. So, that is what it is, all right. Now, let me give you the critical Reynolds number for various flows, which may be useful as we talk about turbulent flow. Okay. So, let me just quickly sketch those numbers. Flows, then sketch of the flow, and Re critical. Okay. So, stagnation point flow. Okay. Stagnation point flow. For this particular case, stagnation point flow means, let us say there is a surface and there is a flow which is coming and directly hitting. Then this is what is your sort of streamline pattern. Okay. This is what is your streamline pattern, and Re critical for this particular case is 12490. Okay. All right. Now, for boundary layer flow or Blasius flow, okay, that means boundary layer flow at 0 pressure gradient. Blasius flow, okay. Blasius flow is nothing but your boundary layer flow. So, this is what is your Blasius flow, okay. And for this it is 520, and separating flow, separating flow often includes a point of inflection. For example, if you consider this is what it is. Okay. So, for this case this is very less, you see 67, and pipe flow that means circular pipe flow, that is what we are talking about. Okay. So, for circular pipe flow it is infinity, that means for circular pipe flow as per linear stability analysis it is stable, but Reynolds experiment shows us that actually it is not so. So, that means that linear stability may not be the ultimate answer, okay, for that particular case. Anyway, then channel flow. Channel flow or plane Poiseuille flow. What you write channel flow, okay. So, that is also something similar like this, and the velocity profile is parabolic for both the cases, but one is circular and another is your. So, this is for this particular case it is 5772, okay. And jet flow, as I have already mentioned, 4, wake flow 4, and shear flows free or mixing layer it is 0. Okay. So, these are the various numbers, okay. But anyway, the critical Reynolds number only tell us from that Reynolds number onwards there is a possibility that a wave will grow. Okay. It does not tell us after the growth what is going to happen. Okay. That we cannot capture using linear stability theory. Linear stability theory only shows after a particular Reynolds number whether the disturbance is going to grow or decay. Okay. That is what it is. For example, there is a flow over a plate and let us say you are introducing a particular wave, you are able to introduce a particular wave of some particular frequency at Reynolds number beyond 520 in a boundary layer flow at 0 pressure gradient. Okay. And you are able to introduce the disturbance beyond the critical Reynolds number. That means that particular wave then will slowly grow, but after growing what is going to happen? That answer cannot be obtained from linear stability analysis. Okay. So, for that to find it out, we have to understand some sort of nonlinear instability, but which is not that tractable. All right. So, any wave let us say which is growing exponentially, let us say for it is growing sort of exponentially. See, if you see this, see the amplitude, see this amplitude will grow exponentially. Okay. So, this amplitude is growing exponentially with space for this particular case if the disturbance is introduced at some Reynolds number which is beyond the critical Reynolds number. Okay. So, in that case it only says the amplitude of the wave will grow, but when the amplitude of this wave is going to grow, what it is going to do? If amplitude is increasing, then what it will happen? It will start triggering the nonlinearity in the flow. How? You can remember in the linear stability analysis we have linearized the disturbance equation. While linearizing the disturbance equation, we have forgotten various nonlinear term in the equations. Okay. So, in that case when the disturbance amplitude is pretty much high, the nonlinear term cannot be forgotten from the disturbance equation. Okay. So, that approximation of linearization fails. Okay. So, in that is therefore, the linear stability cannot predict the next stage of the disturbance growth or your transition rather. Okay. So, how this a particular wave, let us say a particular frequency or a particular wave length, a particular wave length you have introduced, okay, or two wavelength you have introduced of same frequency, then what is going to happen? If we would like to see that, let us take a cartoon to understand how nonlinearity can generate another scale in a flow or different scale in a flow. So, to do that, let us consider the Burger's equation. Okay. So, Burger's equation. So, Burger's equation, let us write this as it can be thought of a cartoon of Navier-Stokes equation, because the nonlinear term is there, unsteady term is there, and you have the viscous term as well. Okay. A simplified form of that you can consider. Okay. So, now let us consider this equation we can write using the u value as capital U plus u prime. Okay. So, let us say capital U plus u prime. So, we have perturbed that flow little bit, so that that u can be replaced with some constant value u plus some perturbation u prime. Okay. Del t plus u prime del u plus u prime del x is equal to nu del 2 u plus u prime del x 2. Okay. Where small u is nothing but your u plus u prime. This is let us say constant and this is the disturbance. Okay. So, if capital U, which is a constant if we consider just for simplicity, then we can write this part as u prime del t, because del u capital del t, u is a constant, so that should be 0. Similarly, from here what we can get that this is the first two, I mean if you multiply. So, this into del u del capital U del x, that is 0. So, then you are left with only one term when you multiply by this with the derivative term, and that is your this term plus another term you get which is non-zero. See, if you multiply u prime del u del x del capital U del x, that is also 0 because capital U is constant. So, you are left with another term, that is u prime del x, and in the right hand side you are left with del 2 u prime del x 2. This is because of the fact u is constant. Okay. So, if this is the case, now let us consider that u is periodic in space. Okay. U is a function of time and space both here, sorry, u prime is a function of both time and space. So, let us consider it is periodic in space. Okay. The disturbance is periodic in space. So, that means u prime periodic in space means from Fourier series we can call it as a k of t, amplitude is a function of time here, and exponential I k alpha x, okay, where this a k equals to a minus k star. Okay. This we have already talked about the Fourier series in the last class and its complex representation. Whoever are not familiar with, kindly go to any standard book, this particular expression should be standard mathematical book, this particular expression, or mathematical engineering book, this particular expression should be available. Here k is an index, alpha is wave number, keep it in mind, alpha is wave number, k is an index here. Okay. So, alpha is wave number and k is an index. Okay. So, with this expression, now if we plug this expression in this particular equation, what we come up with? We can do another step before we capital U del u prime del x plus this minus nu. Let me take all the linear term in the left hand side, okay, and the non-linear term let us take in the right hand side before we do any manipulation with the previous equation. Okay. Now, using the expression of u prime is equal to minus infinity to infinity a k exponential I k alpha x, we get, what do we get? Summation minus infinity to infinity dA dt. Okay. The first term, it is the temporal term here. So, if you have a derivative, it is going to be derivative of the coefficient which is function of time into the exponential term. Okay. The next one, I alpha k capital U, I alpha k capital U a k into the exponential term which we are not writing, and here the minus nu minus nu double derivative. So, that is going to be your minus nu I square k square alpha square a k. Okay. So, into exponential I k alpha x equals to minus alpha, sorry, minus infinity to plus infinity. Here let us do one thing, this is the nonlinear term. So, this and this expression, instead of using k here, just to identify how they are interacting each other, k is just an index here. So, this index anyway can be anything, can be m, can be n, can be other things as well. So, that k, instead of writing k, we can write for this one as m, for this particular one we can consider this to be m, okay. Just to see how the interaction is going to happen, because this is the nonlinear term. So, if we do that, so u prime, so that is nothing but your a m exponential I m alpha x, and this one is going to be minus infinity to infinity. This one is going to be your, if you have the derivative with n keeping it here. So, considering this particular expression, that index is n instead of k here, then we can write I n alpha, I n alpha, and this minus is there, there should be a minus here, I n alpha, and here it is going to be n, okay, into the exponential I n alpha x, okay. So, this is what we get it. So, this is what we get it. Now, let us do one thing, this particular expression we can write as, you see this particular expression summation minus infinity to infinity d a k dt plus I k alpha u a k I square minus 1 plus, so k alpha square nu k alpha square a k, okay, exponential I k alpha x equals to minus we can write this as minus m minus infinity to infinity, and here minus infinity to infinity I n alpha a n into, you see this exponential and then exponential together, let us write it as I m plus n alpha x, okay. So, this equation this equation is going to give us a solution when this exponential term in both the side are going to be equal, okay. That means this equality says that k is equal to m plus n, okay. That is what it says. If this is the case, then we can write this equation as, okay, or minus infinity, or this can be written as d a k dt plus I u k into alpha a of k plus nu k into alpha whole square a of k, okay, equals to we can finally write this as minus infinity to infinity, this is I n alpha I n alpha into a n and a m. So, that can be written as a n and a m can be replaced with k minus m, okay. Sorry, k minus n. So, this is what finally we can write. Okay. Now, let us do one thing. Let us say we have considered a wave with only plus minus a 1 not is equal to 0. For all other amplitude is considered to be 0. For example, let us consider a plus minus a 2 is equal to 0, then plus minus a 3 is equal to 0 and so on. Okay. We have considered a 1 is equal to 0 or a 0 plus a 0 is equal to 0. We have considered all are 0 except this amplitude of k is equal to 1 and n is equal to 1, sorry, n is equal to 1 wave number. Okay. Only a 1, that is what is considered. Okay. If this is the case, then you see, if this is the case, that means what we are doing, m is equal to 1 we are considering, n is equal to 1 we are considering. We are considering m is equal to 1 and n is equal to 1. That means our k is going to be m plus n, means k is going to be 2, right. So, if this is the case, you see, then from this above equation what we can write, okay, considering this you can write, then you see dA2 dt plus IU, this is 2 alpha A2 plus nu 2 alpha square A2, okay, equals to what do you get? Here the summation is not going to be there at all, because anyway you are considering m is equal to 1, n is equal to 1. So, that is what is going to be I alpha your A1, this is also A1. That means, because all other are 0, if you get this summation for all other cases is 0, only 1, this is what is left with. That means, with this non-zero, what you are getting? You are getting another mode of 2 alpha. You have considered only one mode of alpha, you are getting another mode 2 alpha with some non-zero A2. Although initially I considered the value of A2 to be 0, due to this nonlinear interaction between A1 and A1, you are able to get some non-zero value of A2. So, that means this non-zero value of A2 is coming due to the nonlinear interaction from this particular side. Okay. So, that means the nonlinear interaction between this wave or between nonlinear interaction of a wave alpha is generating another wave of 2 alpha, correct. Okay. So, this is what is the output of the nonlinear interaction. So, as a result A2 is becoming non-zero, although you started with A2 is equal to 0, but due to this interaction A2 is going to be non-zero. Okay. So, that means when a particular, let us say 50 hertz frequency have inserted in a flow and that frequency started to grow in the downstream direction. Due to nonlinear interaction, that 50 hertz can generate another frequency of 100 hertz, another frequency of 150 hertz and so on, because this A1 will interact with A2 now and generate another wave which will excite A3 and so on. Okay. So, that is the nonlinearity. That means what? Although the linear stability is saying us that from which point of time or point of space the wave is going to grow with time or space, ultimately it cannot predict the end state of that. That is all because of the fact that wave, when it will grow to some value, it will start interacting nonlinearly among themselves and try to excite some other harmonics in the flow or other waves in the flow. As a result, energy will be redistributed. Okay. So, therefore, when you will see initially your amplitude may be exponentially increasing, but after some time that exponential increase of energy will be flattening. That is all because of the fact that energy is getting redistributed to various modes due to this nonlinear interaction. Okay. So, that is what the point is. Anyway, so that means we understand the stability analysis can give us the Reynolds number from which point a flow can amplify a disturbance, and after some time when that amplitude of that wave will be sufficiently high, the due to nonlinear interaction other frequencies comes in the flow. Okay. That is what we till now learned. Okay. Then how? See, our ultimate goal is to predict the transition at what particular location the flow is going to transition to turbulent. That is what our main goal. Then how to find that? Actually, there is no clear cut model to predict that. Okay. We do have some correlations, for example, Mickel correlation for boundary layer flow or semi empirical formula based on this e to the power n method. These are the things which are available. Okay. But we do not have a proper mathematical basis to predict transition, because flow transition depends on many parameters. For example, boundary layer flow, the transition of boundary layer flow depends not only the surface roughness, surface curvature, pressure gradient, then free stream disturbance, then compressibility. There are many sound. So, there are many aspects of transition, many parameters involved in a particular transitional flow. Therefore, it is really very difficult to devise a transitional or transition model. Okay. So, for a particular flow you can have some sort of empirical model based on which you can predict transition. Okay. Means the point from which the point from which onward the flow will be turbulent. Okay. So, let me just quickly cover this particular part and finish. Our main aim is transition. So, how we can predict transition. Okay. So, or transition Reynolds number, that is very important. Okay. So, the transition Reynolds number is really very difficult to predict, because the transition depends on many parameters as I have mentioned. Okay. And there are many types of transition, for example, natural transition, bypass transition, separated flow transition. So, it is really very difficult to predict transition for different flows. Okay. So, that is the ultimate game of the stability analysis. Okay. Now, there are some correlation based on which transition are predicts. So, something called Mickel correlation. Okay. So, this is for boundary layer transition, keep it in mind. Okay. So, for that it is proposed that Re theta is equal to when it is approximately 2.9 into Re x transition to the power 4. So, what it says, when your Re theta will be equal to this, or Re theta related to Re x transition in this particular way, that particular location indicates a transition. That means, suppose you ln Re theta versus you plot ln Re x transition. If you plot that, if you start calculating your Re theta value, okay, whenever this Re theta value will come and sit in this line, that is what is your point of transition. Okay. When your Re theta value will come and sit in this particular line, that is what is your transition location. How we can calculate this Re theta value? So, there are proper way to calculate Re theta. Re theta means Reynolds number based on momentum thickness. So, Re theta is defined as u, which is a function of x or can be a function of x, theta can be a function of x divided by nu. So, using there are some methods called Thwaites method, for example. Okay. Thwaite methods, using which you can calculate this Re theta value, okay, till you get this equation satisfied. Okay. So, at that location, I mean wherever it matches this particular relation, that is the location for your transition. So, this is one correlation method. There are many such correlation methods. Another method, semi empirical method, for example, that is your based on linear stability. So, let me just explain quickly what it is. So, semi empirical method based on linear stability theory. Okay. So, this is something, for example, this is alpha versus Re or x, okay, whatever it is, because both are related, and this is what let us say the linear stability neutral stability curve. Okay. So, any wave let us say of frequency f1, which is going to be amplified within this regime. So, if we draw this, so this is what is your this is what is your minus alpha I. So, this is basically the value will change something like that. Now, if you calculate this minus alpha I dx integral of this integral alpha I, that is from x naught to x value, let us say. Okay. So, this particular value if you calculate, so this integral if you calculate, this integral is going to be something like this. Okay. What is this integral? If you can remember in the last class that ay dy dx 1 by a is equal to, we define this is equal to was our growth rate. This is what it is. So, if you calculate so this particular value, then this particular axis is nothing but a by a naught. Okay. So, now let us say you are given a flow and you would like to find out the transition Reynolds number for this flow, then what do? You first find out this curve, then keep integrating for various frequencies. Okay. If you do this exercise for various frequencies and if you plot it here, let us say this is what is your ln a y a naught. Okay. So, for various frequencies if you calculate, then it is going to come something like this. Okay. So, this is the lower frequency this side. So, higher frequency will come this side, and this is the kind of your maxima. Okay. And it has been proposed that wherever this value is going to be about 10, okay, wherever this value is going to be 10, that is what the location of transition. Okay. Wherever this particular value is going to be 10. Okay. So, that means when your amplification is going to be of the order of e to the power 10, that is the location of your transition. So, that is sort of semi empirical, because you are calculating the growth rate or amplification based on the linear stability, then based on your data you are trying to say that basically it has been that e to the power 10 or 9 to 10 it is, if it is temporal theory it is considered to be 9, if it is spatial theory then it is about 10. So, this particular value is coming from the data, experimental data. So, that is why it is called semi empirical. So, when this value is going to be 10 or at the location where this value is going to come as 10, that is what is your point of transition. Okay. So, we would like to stop here with this. I will again talk about some of these things in the next class. Okay. Thank you.